Okay, hi everyone. We now have the last case remaining. We want to look at circles that are not passing through center of inversion or circles that are not orthogonal to the circle of inversions, and we want to see how these circles transform under inversion. Okay, but to do that we need to take a slight detour. Okay, and I'm going to follow a proof due to Coxeter, one of the best geometers I know, and I like his proof because he sort of helps you locate the center and the radius of the inverted circle. Okay, this is one of the few methods that does it as far as I know. So let's just actually, and that too, importantly, it does it through pure geometry. Okay, so for that we need to go through a little bit of detour called dilations. So let's discuss dilations now. Okay, in this video. So dilations for now. Dilations. If you guys want to look at dilations and its properties and investigate that, you can also ask me for a separate video in the comments, and maybe I will make a separate video on it. Okay. All right. For now, we're just going to do enough dilations to help us solve the final inversion problem. All right. So let's start with what is a dilation. A dilation, roughly speaking, is just a way to zoom out the entire plane from a given point. Okay. Start from a point called the center of dilation, and from that point you try to zoom out everything, or zoom in everything, or whatever. So essentially sort of scaling everything out. So here is the let k be a real number. Okay, for now we can assume it's positive, because if k is negative you generally think of it as a half turn and then a dilation. For now, if you want, we can assume it's positive. Okay, what we'll do is if k is let k be a real number, let's keep it in general, and let O be a given point. Let O be a given point on the plane. Okay. Okay. Now the dilation of the plane the Euclidean plane, that is the flat plane that we have in front of us, the board for example, that's what I'm talking about. The dilation of such a plane with respect to O with dilation factor k, okay, this number k is denoted by d of, I'll just denote it by d of O comma k. Okay, d of O comma k is a transformation. I have not yet defined what it is. I've just defined a symbol for you. So if you have the plane, you pick a point O. What the dilation does is it moves points of the plane to some other point p bar. Okay, along the line. Okay, so O, P and P bar are on a line. Okay, now what is the relation between P and P bar? I have to tell you. Okay, so such that, so with respect to the dilation factor is denoted by d of k, and d of O comma k sends a point P on the plane to P bar. P bar is another point. It sends P to P bar, where the relation is the following. You take OP bar. Okay, this should equal k times OP. Okay, and further, and it's not enough to just say that the length OP bar is k times OP. I have to tell you where it lies. So it actually lies on the line OP, and further P bar lies on the line OP. Line OP. There's a small caveat here. If k is negative, because I said real number, it can be negative. If k is negative, you should think of P bar lying on the opposite side. So in other words, you should, you're not going to worry about it much now, but if you take O, and if you have P, and k is like -2 or something like that, some negative value, then we are going to basically scale. P bar will be here in such a way that OP bar, the length is 2 times OP length, but it's not I mean, if k were 2, then p bar would be here. OP bar is 2 times OP. But if k is minus 2, you have to go the other way. So multiplying by minus 1 has the effect of doing a half turn. And after that, you just scale. Okay. So that's essentially the idea. Okay. All right. So this is what a dilation is. A dilation takes a point P and scales it off by a factor of k and sends it to p bar. Okay. Now this is a dilation. Now what are some properties of dilation? Let's see some properties of dilation. So one of the cool properties is that if you take a point O and if you take a point A and under dilation, let's say it goes to A bar, and on the other hand, supposing you take a point B and you take, after dilation you go to B bar, I mean you're basically dilated with the factor K, okay? Both are, I mean A goes to A bar under dilation DO comma K and B goes to B bar under DO comma K. Then we note something very interesting. We see that OA bar by OA is K, that's by definition, right? That's how we dilate. And similarly OB bar by OB is also K. But here this is very familiar. You have two lines and you have points AB and A bar B bar, and OA bar by OA equals OB bar by OB. You've seen this before. It's basically it tells you by converse of basic proportionality theorem that A bar and B bar are actually parallel. So this implies, this is in fact equivalent to A bar B bar is parallel to AB and A bar B bar is equal to K times AB. Okay? So it just follows from basic proportionality theorem. So what's the basically summary? So if you try to dilate all the points of the plane from a point O with a factor of some certain factor of K, it doesn't matter actually what the factors are and so on. If you try to just dilate any point, I mean the plane about a point, then if A goes to A bar and B goes to B bar, then the segment AB goes to the whole segment A bar B bar. Okay, the segments entirely go, and further the segment A bar B bar is K times the segment AB. This has a very important consequence for us. That is, if you pick the midpoint M, we have already shown that the segment AB entirely goes to A bar B bar. So if you take the midpoint M and join and extend it here, okay, since the segment AB goes to entirely to A bar B bar, M must go correspondingly to M bar because that point lies on this line, the transformed line segment. So M goes to M bar. Now if M is the midpoint of AB, okay, then notice that we can argue that M bar must be the midpoint of A bar B bar. The reason is pretty simple. You can see that A goes to A bar and M goes to M bar, and you have essentially OA bar here. This K is also equal to OM bar by OM. Okay, and applying this logic, we can argue that A bar M bar is equal to K times AM. Okay, but notice AM is actually AB by 2. Okay, AM is actually AB by 2, and we know that A bar B bar by 2. So basically we know that KAB is equal to A bar B bar by 2. I mean KAB we know is A bar B bar already. I mean A bar B bar by 2. So we know that A bar M bar must be A bar B bar by 2, which means that M bar must be the midpoint of A bar B bar. Okay. So what is the moral of the story? The moral of the story is that midpoints of the and segments go to segments, which are parallel segments, and the lengths get scaled by the same amount, but midpoints go to midpoints of the segments. Okay, that's important for us. All right. So under dilation, midpoints of segments go to segments. They carry midpoints with them. Okay, that is the summary. All right, actually it's not just midpoints. You can argue any section, like you can divide in the ratio 2:1, 7:5, whatever. It'll also go to the corresponding 7:5 point on that segment. Okay, I didn't do that because I don't need it for my inversion discussion. Now let's move on to seeing what dilation does to circles. Okay, so if you take a circle, let DO, K be a dilation. Let DO, K be a dilation, and let circle let P, Q, R, S be 4 points on a circle omega, 4 points on a circle omega. So I want to know how the circle omega transforms under dilation. So take that point omega, pick 4 points on that circle. Let's the 4 points be P, Q, R, S. Now I want to know what happens under dilation. Okay, so let's try to see first of all. Okay, not any P, Q, R, S. I think I have to be careful. So let P, Q, R, S be 4 points on a circle omega such that, okay, O, P, Q are collinear and O, R, S are collinear. Okay, what I mean to say is, given a circle omega and a point O, I want to know how omega dilates. To do that, what you do is you just draw two lines, okay, passing through O and which cuts the circle at P and Q and R and S. Okay. Now notice, we know from power of a point that, or the intersecting secant theorem, that OP into OQ must equal OR into OS. Okay, we know OP into OQ must equal OR into OS. Okay. Now here is the cool fact. Under dilation by K, we know that we can just scale everything by K units. So let's multiply this entire equation by K square. If you do it by K square, I can say KOP into KOQ equal to KOR into KOS. Okay, I just multiply by K square. But we know that KOP is OP bar and KOQ is OQ bar. This is KOR is OR bar and this is OS bar. So the P bar, Q bar, R bar, S bar. So the P bar will be somewhere here, Q bar will be somewhere here, under dilation and S bar. We don't know what those 4 points are, they'll go somewhere, but they'll definitely, we know that P bar and Q bar are on the same line by definition. That's how dilation works. So now we have these 4 points, but we proved that OP bar into OQ bar is OR bar into OS bar, which means that P bar, Q bar, R bar, S bar must be concyclic. Okay, must be concyclic. So we proved that if you pick any 4 points on a circle, when you dilate it, it goes to some other 4 points which are also on a circle. They are concyclic. Okay. Now here is the interesting thing. We want to prove now. So circles go to circles, but the point is, how do you know what can you say about the centers and radius? So I claim the centers also go to the center. And once centers go to centers, we can use the previous observation to say that if you join P to C and P bar to C bar, they must be collinear. They must be parallel, and P bar C bar must be K times PC. But PC is the radius, so the radius must become K times. Okay, if the radius here is R, the radius on this side is K times R. So when you dilate a circle, essentially the centers go to the center and the circle's radius becomes K times, okay, the original radius. Alright, so this is a fact that will be extremely useful for us in the second inversion part, the last remaining inversion thing to prove.